Hello students, welcome to lecture 33 of the online course on Nanophotonics, Plasmonics and Metamaterials. Today's lecture will be on alternative plasmonic materials. So here is the lecture outline. We'll quickly give a overview of this topic, then we will discuss about the limitations of conventional plasmonic materials. We'll discuss some elusive lossless materials which are basically difficult to find. Then semiconductors to metals, we will look for metals to dilute metals, how they are relevant as alternative plasmonic materials. We will also discuss some 2D plasmonic materials and then we will conclude. So here is the overview. Materials technology has played a significant role in human history across different areas and different eras, which enabled creation of novel applications that in turn contribute to the exploration of new scientific knowledge. Advancement in scientific concepts often drive the development of more advanced material technologies. This has been exemplified by the transition from Bronze Age to Iron Age, and this has basically marked the progress in metallurgy. The relationship between science and technology, they form a positive feedback loop with materials playing a critical role in this mutually reinforcing process. Two significant examples that we can cite from the past century are basically the semiconductor technologies and optical communication, both of which have had a transformative impact on our ability to handle information. So it is the blessings from semiconductor technology that we are able to do the computation very fast, and the optical communication that allows the transfer of data at a lightning speed. So these two has actually impacted a lot. In recent decades, the processing speeds for handling information have experienced exponential growth, and that is primarily driven by the scaling of semiconductor electronic components. So if you think of this trend is was predicted by Moore's law, okay, this particular scaling trend, that the number of transistors in a chip will double every 1.5 years or 2 years, okay. So this advancement in semiconductor technology and optical communication, they have basically revolutionized the way we process information, we transfer information in this modern digital age. So we have seen transistors scaling down from 200 nanometer to 35 to 1.8 micron even nanometer. So that has actually gone down to very tiny channel length size, and that has allowed amazing miniaturization, okay, and it has also given very high operational speed. Now when you think of further extensive scaling, so till 35 nanometer or a bit that was achieved in the last decade, okay, till then those effects like short channel effect, gate leakage and dramatic increase in power density, they were not that significant, but then with further extensive scaling you will be starting to see all these effects coming into picture. Now these difficulties highlights the complexities and limitation associated with pushing the boundary of the semiconductor transistor miniaturization, okay. So this is where you will find a problem with the miniaturization, and we have also already discussed that plasmonic can be an alternative technology which already has gathered a lot of interest as a potential solution to overcome some of these challenges by increasing the information processing speed, okay. And plasmonics, when you combine this with the fields like metamaterials and transformation optics, they have significant expansion over the last couple of years or last one decade you can say, and they have given the hope that lot of new exciting physical or optical phenomena can be realized using these technologies, and people have demonstrated different application prototype. They are not commercially available, but they are still in the research laboratories, and people are able to demonstrate different capabilities of these technologies, and they are really promising. Now, to translate these innovative concepts and prototypes into practical technologies, this is where material technology will be playing a crucial role. Okay? So, you want to achieve desired properties in plasmonics and metamaterials, and they actually rely heavily on the engineering of the constituent materials. So, that brings in the importance of the material science in these domains or in these areas. Now, plasmonics has gained significant recent attention, okay, though the initial the first demonstration of plasmonic effects were like age old. So, if you can remember the Liker gas cup or the stained glasses, those are seen in the medieval cathedrals, okay, those were the first instances where plasmonic effect could be seen. Okay. Still, people are exploring plasmonics in this new digital era, because that can actually help you in overcoming the limitations of both semiconductor electronics as well as dielectric photonics, and can give you the best of the both worlds. Something like you can get the critical dimension of the device almost below 10 nanometer, and you can still target operating speed above 1 terahertz. So, this can be done by breaking the limitation of the diffraction of the conventional optical system. That is what dielectric photonics faces the challenge. This is the typical diffraction limit of light. So, optical communication being the fastest means of information processing, okay, they are having this problem of miniaturization, and this is where plasmonics can help. Okay. So, plasmonics can get you the size below the diffraction limit. So, we have seen this already. This is a example of how you can excite surface plasmon polariton propagating along a metal dielectric interface when some light is falling. Okay, but the one thing is not shown here is that it cannot be directly excited by simply shining light on the interface. You have to have a arrangement of phase matching, either using a prism or a grating. Okay. So, we have seen this, and this is the example of localized surface plasmons which can work without anything. You can simply shine light on it and you can excite localized surface plasmons on this. Okay. So, we have already seen this and they actually allows amplification of local electromagnetic field intensity by several orders, and they have found applications in sensing and scattering, or absorption, enhanced absorption or enhanced scattering kind of phenomena. So, we have also seen that metamaterials are basically engineered artificial materials that can give you new optical properties, and we know that the meta atoms or meta molecules are designed to be much sub-wavelength, that is much smaller than the wavelength of light. Now, metamaterials have enabled novel functionalities, something like optical magnetism, sub-diffraction resolution or negative refractive index, and all these things are possible by the materials themselves. Like if you take metals, they exhibit a negative real permittivity at optical frequencies, whereas at optical frequencies dielectrics have a positive permittivity, right. And metals, they introduce optical loss due to their electronic transitions, and that creates a problem at optical frequencies, because that will limit the performance of the device. So, if there is loss, the device will heat up and you are losing energy because it is simply getting absorbed. Okay. Now, this presents challenge in the design and integration of plasmonic and metamaterial devices. So, if you use the metals, the conventional metals, you are facing issues because of this high loss at the optical frequencies. Now, let us discuss these limitations of conventional plasmonic materials in more details. So, when you think about plasmonic materials, gold and silver should come to your mind immediately. They are the popular choice for plasmonic and optical metamaterial devices due to their low ohmic loss and high DC conductivity. However, when you think at optical frequencies, these metals they exhibit interband transitions which introduce significant losses. Okay? And these losses are in the form of valence electrons absorbing those photons to jump to a higher energy level. These interband transitions are basically responsible for the distinct colors of the metals like copper, gold, okay, and they come from electron energy level shifts. The imaginary part of the gold, so if you remember the gold permittivity that we saw a couple of lectures back, there is a real and there is an imaginary part, and the imaginary part of that permittivity reveals basically two types of losses. One you can call intraband or Drude loss, and the other one is interband loss. Okay? And in this particular diagram you can actually see that the imaginary part of the permittivity is being plotted, okay, and the finely dotted ones that shows the interband transition, and this one shows the intraband transition. And what you can see that the Drude losses, okay, the intraband transitions, they are more prominent in the near infrared regime, but they decrease at shorter wavelength, and at shorter wavelength you can see that interband transitions, they actually dominate and they become the main reason for optical losses. Okay. So, these are this particular interband transitions or the losses at short wavelength for metals like gold and silver, they make those metals less suitable for plasmonic and metamaterial applications. So, people are looking for, scientists are looking for materials which can have reduced interband losses, okay, so that you can overcome this limitation and enhance the performance of the optical devices which operate in this region. So, for applications like transformation optics, it is crucial for metals imaginary function to have low values indicating minimal loss that we have seen, right. If you want to match the permittivities, okay, of the metal and the dielectric part, and dielectric is more or less lossless, okay. So, you want metal which should have negligible amount of loss, then only you should be able to match the permittivity between metal and dielectric, and that should help you in transformation optic devices like cloaks or other ones. Okay. Now, the imaginary, we understand that the imaginary part of the permittivity is basically influenced by three loss mechanisms. So, one is the interband transition, the other one is intraband or the Drude, and the third one is the scattering loss that comes from the defect within solid structure. So, we can actually look into that also in more details. So, here is the real and imaginary part of permittivity for silver. Okay. Now, if the interband transitions are absent in a metal, then the intraband and scattering losses from the defects, they will contribute to the significant overall loss, okay, and they will pose a challenge to the device performance. Okay. So, here we can see how the electrons are behaving in metal. Okay. So, it has been, you have used a Drude model to explain the behavior of the electrons in this metal. So, here we have considered silver. So, the permittivity is written as real and the imaginary part, and then there are two components here. So, one is the real part, this is the imaginary part, and in the real part you actually can see there is epsilon b, which is frequency independent, and this is called as the polarization response from the core electrons, or you can simply call it as background permittivity. Here omega p is the plasma frequency and gamma is the Drude relaxation rate. So when you plot this, you see this is how the dots show you how exactly these are the real values, okay, the dots one, the experimentally measured values, and the curved line over here that comes from this particular equation. On the other side, this is basically the imaginary part, that is epsilon double prime, and you can see that also closely follows the experimental data till a particular wavelength or energy range. Okay. Now, what is important here to note that the root relaxation rate, that is the gamma, it actually plays a role in the scattering or ohmic loss, okay, because it directly affecting the imaginary part of the permittivity, which is epsilon double prime, right. Now, if you want epsilon double prime to be really small, if you want this part to be really small, okay, then you should reduce gamma, okay, and that means you have to decrease the carrier concentration n, or ideally both, okay. So, if you are able to do that, that will bring down your imaginary part. Now, the efforts to reduce gamma, which is basically the relaxation rate, okay, in conventional plasmonic materials like the noble metals, gold or silver, that can be achieved through cryogenic cooling, but that has not yielded sufficient amount of loss reduction for practical devices. So, that did not work out. Okay. So, once again, what is the method of making this imaginary part small? You can reduce gamma by decreasing the carrier concentration. Okay. These are the two methods. Okay. So, either you decrease this or both simultaneously. Okay. So, here what has been seen, that for noble metals or materials, they have very high carrier concentration, and that is why and this further increases epsilon double prime in the NIR and visible range. So, lowering the concentration in this metal would be very beneficial for reducing this epsilon double prime magnitude. Okay. So, what we are planning to actually reduce the carrier concentration in the metal. That should give you lower imaginary part of the permittivity. Now, because the conventional plasmonic materials with like gold, silver, they suffer from high loss, okay. They have significant issues in applications in plasmonics, then optical metamaterials and transformation optics. It's understood, because if you design a waveguide using this kind of plasmonic materials, because of the loss, the propagation length will be very short. Okay, so that will not help you. Although you are able to confine energy in a very tiny space, you will not be able to take that energy further because of this kind of material loss, which are intrinsic. Okay. And another challenge will arise from this kind of real part. Okay, large magnitude of this material will be in the transformation optic devices. So, transformation optic devices, you have seen that metal dielectric, okay, you should not have very large singular values. Okay. Now, if you actually make your epsilon very low, epsilon double prime very small, okay, in that case another challenge will come from this exceptionally large magnitude of the real part of the permittivity. Okay. So, usually in this particular materials, okay, in this material like gold and silver, the real part of the permittivity is very high, and that will make your life difficult when you want to realize a transformation optics device. Another challenge arises from the exceptionally large magnitude of the real part of permittivity in these metals, making it difficult to design transformation optics device. When the real parts of the permittivity of the metal and dielectric are of the same magnitude, it is easier to tune for the geometric field fraction to design some required specification. But if because dielectric does not have this imaginary part in the permittivity. So, if the metal has got that, it makes it very difficult to obtain the correct geometric filling factor. On the other hand, if the metal's real part is significantly larger than that of the dielectric, it requires using very small metal inclusion within the metamaterials, okay, or metamolecules in a metamaterial design, and that because this kind of very small metal inclusions makes it very difficult for the nanofabrication. Okay, so there will be fabrication challenges in this case. Therefore, having plasmonic materials with smaller magnitude of epsilon prime, that is the real part of permittivity, would offer distinct advantages in numerous application while simplifying the design of your structure. Also, it will simplify the fabrication processes. So, we understood that novel metals pose a significant technical challenge and they are not compatible with the standard silicon manufacturing processes. So, these limitations actually hinders the utilization of plasmonic and metamaterial devices in conjunction with the common nanofabrication technologies. Also, the incompatibility limits the potential integration of the plasmonic and metamaterial components with the nanoelectronic devices, and that restricts the development of advanced hybrid technologies. So, you can understand that the issue is with the material which show these plasmonic properties. The incompatibility issue with the noble metals arises from their tendency to diffuse into into silicon, forming deep traps, and this diffusion negatively impacts the performance of nanoelectronic devices. So, that is a problem. So, integrating novel metals into silicon manufacturing process becomes a very complex task due to the diffusion issue, and it makes it very difficult to achieve without specialized processing steps. So, you have to incorporate some extra care into the fabrication process to handle this. While copper has been incorporated into silicon processes, it still requires additional steps to establish diffusion barriers between silicon and copper, which actually limits the ease of integration. Now, despite all these advancements, gold and silver still remain impractical for integration into silicon manufacturing processes, okay, and these are due to the challenges associated with this novel metals, okay, in these technologies. So, with all these shortcomings of the conventional plasmonic materials, researchers have been motivated to search for better alternatives. So, many alternatives to metal have been proposed that can overcome one or more of drawbacks that have been mentioned till now. The significance of choosing an alternative plasmonic material depends on the end application. So, this is very important. So, you need to know what application you are looking for. There is no one size fit all kind of thing. So, depending on the application, you can choose the right alternative material, okay, and we will discuss the general criteria, okay, on how to choose materials in this lecture. So, we have been looking for alternative to metals in a lossless metal, okay, which is bit elusive, difficult to find, okay, but that is an ideal candidate that can replace the metals in plasmonic and metamaterial devices. So, what we are looking for? We are looking for purely real and negative permittivity, that is your epsilon double prime, the imaginary part is 0 and the real part is negative, okay. So, this is the best kind of metal you can think of, which will give you metallic response, but no loss, okay. But such a metal okay, is like, although this kind of material would be like highly desirable for various applications, but achieving this kind of thing, that you zero loss and negative permittivity simultaneously for all the frequencies, in any dispersive material is impossible due to the causality condition, okay, and that basically limits the feasibility of such ideal material. So, the real and the imaginary part of the permittivity, they are related by Kramers-Kronig relationship, which we are not discussing here in detail, but I just wanted to tell you that this relation tells you that these two components are tied together. Okay. So, if one is made too small, the other one will become very large, okay, like that. So, let us now think of this material, okay, without loss, how things will look like. Okay. So, here this particular figure shows two possible electronic band structure for a metal. So, this one has got loss and this one is lossless for a specific wavelength range. Okay. So, this figure A resembles the typical band structure of many common metals, and figure B is basically a hypothetical band structure of unique metal, and this is typically a lossless metal. Okay. So, here in this particular figure you are able to see three things. First, you can see a completely filled valence band, then you can see a incompletely filled conduction band 1, and then you can also see a completely empty conduction band 2. Okay. So, what happens when photons with energy less than EC1 prime minus EC1, this gap, okay, that can cause intraband transitions, and that is labeled as 1, okay, in CB1, is leading to significant optical loss, okay, which is very similar to the Drude metals at low frequencies. Now, if you see that when the photon energy slightly exceeds this EC1 EC1 prime minus EC1, okay, if the photon energy is slightly larger than these, okay, they will end up going here, and this is not allowed. Okay. So, that is the case where you do not have any transition, okay, and this situation is very unique, and this does not happen here, okay, because here you will find a within the conduction band there are empty levels, but here because you are able to have this gap, these are not allowed levels. Okay. So, the lossless regime actually persists as long as the photon energy is less than the lower of EC2 prime minus EF. So, this gap and EF minus EV. Okay. So, as long as the photon energy is less than the minimum of these two, you will end up having this kind of a transition which is not allowed. So, the photon energy is not basically absorbed. So, this is happening because there are no allowed electronic transitions, and that is because of the unavailability of the energy states, and this results in a zero optical losses. So, you can understand this can happen over a specific wavelength range. So, depending on your application or the required application range, you can think of materials which can have this kind of band structure, but again this is a hypothetical one. Okay. Now, the optical losses will return for energies larger than EC2 prime minus EF, okay, and EF minus EV due to interband transitions from CB1 to CB2, that is your this number 4. So, this one shows interband transition, okay, from CB1 to CB2, okay, and also you can have this transition which is from VV to CB1, that is labeled as 5. So, intraband transitions at low photon energies produce a polarization response that typically generate a negative real permittivity, while the unit band structure here can lead to zero loss within a specific range of photon energies, okay, and this is the range over which, okay, there will be no allowed transition. So, the described scenario here tells you that theoretically there could be a possibility of metal where it is completely lossless over a specified range, okay, and this allows you to think of new possibilities for advanced material design. So, the absence of naturally found metals with the required band structure we have just seen, okay, explains why metal in nature always exhibit inherent losses, okay. So, in metal you will have this, the natural metal will look like this. So, here all these bands will get accepted and then you will have those losses, okay. So, Kurgin and Son proposed in this particular paper, they proposed the stretching of the lattice of a sodium metal by nearly a factor of 2 could achieve metallic behavior, that is real part of permittivity to be negative and lossless in a particular spectrum, that is in mid IR 1.8 micron to 2.4 micron, okay. Although the practicability of this concept remains uncertain. So, they have proposed, but then they could not show it, okay. The paper also suggests techniques to stretch metal lattices for including foreign atoms. For example, aluminum oxide is mentioned as a metallic material with increased inter-aluminum spacing due to the inclusion of oxygen atoms, but such modifications will require careful consideration of their effects on the band structure and also free electron cloud. The addition of foreign atoms can alter the electronic band structures, that we all know, and also the conduction band electron distribution. So, in the case of this aluminum oxide, oxygen nuclei bonding with aluminum electrons, they reduce the concentration of the free electrons in aluminum. Now, despite theoretical proposals and potential lattice modifications, the absence of naturally occurring lossless metals underscores the ongoing challenge of realizing materials with simultaneous losslessness and negative real permittivity, okay, in practical applications. So, there are two possibilities in producing alternative materials based on the Drude description. One, you can think of heavy doping of semiconductors. So, you are basically doping a semiconductor such that it starts behaving like a metal. So, that will introduce a significant number of free carriers in that case, and this process can shift the optical properties of semiconductor towards metallic behavior within a desired wavelength range, and that could enable the plasmonic applications. And the other approach is carrier reduction in metal. So, you have to reduce the excess free carriers in metallic materials through various techniques, and by controlling and reducing the carrier concentration, it will then become possible to tailor the plasmonic properties of metals for specific application over a desired wavelength range. So, there are a few other techniques that can produce low loss metal. One of these techniques is to use or design a material with nearly zero loss that results from electromagnetically induced transparency, EIT. So, what happens in EIT? EIT effect can make materials nearly lossless to specific laser radiation. There the transmission suddenly improves because of a resonance effect, and EIT relies on a nonlinear optical phenomena where one resonance frequency reduces losses when a strong field is applied at another resonance. We will not go into the details of EIT effect, but you can always look for the electromagnetically induced transparency effect in material, and there you can see that it actually becomes lossless at a particular laser radiation. This is a narrowband effect, Okay. So, this effect causes the real permittivity of the material to switch from negative to positive near the resonance frequency with minimal loss. However, as you can see that EIT has limitations, they are inherently narrowband in nature and that depend on specific material properties and electronic structures, and they also require high intensity optical excitation. Various other techniques also exist to reduce losses in metals, but most technically significant ones are those implementable in devices, right. So, another approach would be to alter the plasma frequency of the Drude metals, and that could be a promising and accessible approach without major technical barriers or challenges. So, how you can do that? Two prominent strategies of tailoring metals can be: one, you can convert a semiconductor into a metal through heavy doping, and the second one is to reduce the carrier concentration in metal to decrease this metallic behavior. So, we have actually discussed briefly these two methods. So, we will now look into each of these ideas in bit details, okay, and see what are their applications. So, let us begin with semiconductor to metal. So, we understand that heavy doping of semiconductors can be a method of increasing the carrier concentration and make the semiconductors behave like metals, but they are also actually less metallic metals. Okay. To achieve metal like optical properties, that is, you require the real part of the permittivity to be negative in a specific spectral range. There is a minimum required carrier concentration that can be estimated from the Drude model. So, you have to make sure that you reach that level. Okay. So, the lower limit on n, okay, for achieving negative permittivity at frequencies below plasma frequency, okay, can be taken from this equation. So, omega p square is greater than, should be greater than omega b, omega c square plus gamma square, where n will be, okay, greater than this. So, you have got a limitation. So, this is kind of this has a lower limit that will give you a negative real part of the permittivity at frequencies below the plasma frequency. Okay. So, you are looking for omega less than omega c. So, this is basically the crossover frequency omega c. Okay. And here what are the other things? You are using epsilon naught, okay, that is the vacuum permittivity, is the electron charge, and m star is the effective mass of the carrier, that is electron here. So, doping is a crucial technique for tailoring materials to exhibit desired optical properties and plasmonic behavior. Now, common semiconductors like silicon need a minimum carrier concentration of around 10 to the power 21 per cubic centimeter to exhibit metal like optical properties in the near infrared regime. Now, achieving such high carrier densities require ultra high doping densities, which can present substantial technical challenges and limitations. Another issue to be considered when choosing a semiconductor for creating a metal like behavior will be the mobility of the carriers. Okay. Now, the mobility mu of charge carriers is a critical consideration when you want to select semiconductors for achieving metal like behavior. This is the equation that correlates mobility with the other parameters. Okay. So, you can see that gamma equals E over mu m star. So, to reduce the damping loss, okay, it is important to maximize the mobility and mass, effective mass product. So, the denominator should be as high as possible if you want to reduce the damping loss. So, if you want to transition to silicon plasmonics, that is a possibility, but as we discussed, it will require heavy doping of silicon. so that silicon can exhibit metallic behavior at telecom wavelengths. Okay. But then this high doping presents some challenges. Silicon can be doped as N-type using group 5 elements such as phosphorus, arsenic, antimony, and it can also be doped as P-type with group 3 like boron, aluminum and gallium. And the solid solubility curve for some of these soluble dopants are shown here. Okay. So, here the dopant concentration is shown as a function of temperature, and what you can see here is that the solid solubility, although it is high, the doping efficiency decreases when the doping concentration approaches the solubility limit. Although the lower effective mass of the conduction electrons in silicon compared to the holes, okay, achieving the necessary high N-type doping for silicon to become metallic at telecom wavelengths will be difficult, and that requires research in this solid solubility limits and also the doping efficiency for various dopants. So, here we have seen the group 3 kind of, so it is mixed actually, you have got boron, you have got phosphorus and arsenic. So, it shows different doping concentration and solid solubility for each of this. The next thing we can try with germanium. So, germanium commonly used alongside silicon in electronic devices, it offers high electron mobility, and it has also got a smaller optical band gap. So, it makes it suitable for use as detectors, right. So, you have seen germanium based detectors in telecommunication wavelengths. However, germanium faces absorption issues at telecom frequencies due to interband transitions, and that means it is lossy, and that is challenging for plasmonic applications again. So, the higher dielectric constant epsilon b that you see for germanium when you compare with silicon, that will tell you that it will require even higher doping levels for achieving metallic properties at given wavelength. Okay. So, the solid solubility curve for highly soluble dopants in germanium is shown here, and you can see that germanium has highest gallium has the highest solubility in germanium, followed by aluminum and arsenic. So, if you go back and compare this with silicon, here arsenic had the highest solubility and boron has the lowest one. However, the numbers are nearly an order of magnitude smaller than those of silicon. So, you can actually see the dopant concentration and compare. Hence, it is more challenging to heavily dope germanium to turn it into plasmonic. So, if they are getting saturated, okay, so you cannot dope beyond that, right. So, it means it is difficult to dope germanium to that level you can do for silicon. So, it is difficult to turn it into plasmonic in the optical range. Now, you can also think about 3-5 semiconductors. These 3-5 semiconductors have played an important role in various technologies, something like high speed switching, power electronics, optoelectronics, and that is due to their wide tunability of the band gap through ternary and quaternary compound variations, right. So, if you think of integrating plasmonics and metamaterial devices into optoelectronics platform, okay, that's a very crucial development, and that will make the exploration of plasmonic properties in 3-5 semiconductors highly relevant, okay, for achieving this objective. So, you can think of arsenides and phosphides, okay. So, 3-5 semiconductors including say gallium arsenide and indium phosphide, they offer optical band gaps near infrared, okay. So, they are also potential candidates for plasmonic applications. They have background dielectric constant which is comparable to silicon, and their high electron mobility reduces the carrier concentration requirement for the plasmonic behavior in the near infrared range. However, achieving the necessary high level of doping in these 3-5 semiconductors are challenging due to the lower solid solubilities of dopants and poor doping efficiency. So, though there are some good factors, there are also some challenges. In some 3-5 semiconductors like gallium arsenide, achieving n-type doping beyond 10 to the power 19 per centimeter cube is difficult due to the effects like doping compensation, and p-type doping can actually lead to something above 10 to the power 20, okay, in materials like p-type gallium arsenide, but mu will be larger in this case, right, because mu has higher effective mass and poor carrier mobility. So, that will also not help. So, while we heavily doped in indium arsenide, you can actually see good promise for plasmonic behavior in longer wavelengths. So, this is a good option. However, further increasing the carrier concentration in these materials look challenging, and that limits the application of these materials for plasmonic applications in mid infrared range. You can think of nitrides. Gallium nitride is an emerging platform for optoelectronics, and these are capable of operation across the entire visible spectrum. So, indium gallium arsenide, this ternary system can offer large bandgap tunability, and that is why it has attracted researchers for various optoelectronic applications. So, we can also look for transparent conducting oxides or TCOs. These are basically oxide semiconductors like zinc oxide, cadmium oxide, indium oxide. They can be heavily doped to create transparent conducting oxides. And TCOs are known for their large band gap, and they are transparent in the visible range, and they typically serve as electrical contacts in display panels. Even every smartphone has got TCOs. TCOs can exhibit metal-like optical properties in the near infrared regime due to high DC conductivity, as can be shown in the figure. So, here the real part and here the imaginary part of the TCO films are shown. Okay. So, this one is aluminum doped zinc oxide, this is gallium doped zinc oxide, and this is ITO, indium doped tin oxide. Okay. The optical properties of the TCOs can be tuned by adjusting the carrier concentration of the doping levels. Now, TCO nanoparticles or nanostructures, they can exhibit localized surface plasmon resonance behavior, which you can tune based on the doping levels. Okay. So, you can also deposit a thin film of TCOs on a glass prism, and this can support SPP waves at the TCO air interface, okay, when infrared light is incident from the prism side in the Kratchmann geometry. Okay. Figure B to D actually shows the reflectivity measurement from the prism coupling. Okay. So, here you can see that, and what is important here is that the TCOs can be incorporated into metamaterial design because they are low loss alternatives for negative refraction, okay, and they can be used in tunable plasmonic devices like modulators, switches in near infrared range. So, the other method is metals to dilute metals. So, this is an alternative approach to reduce the optical losses in metal by exploring dilute metals or metallic compounds with lower carrier concentration. So, introducing non-metallic elements into a metal lattice can effectively reduce the carrier concentration, but may also result in altered electronic band structures, and there are potential drawbacks like increased interband absorption losses. So, the research on dilute metals has been limited, but these materials can also offer advantages such as tunability, ease of fabrication and integration, okay, that can outweigh the disadvantages that we mentioned here. So, various classes of less metallic materials such as metal, silicates, germanides, ceramics like oxides, carbides, borides, nitrides and intermetallic, they have also been studied for their optical properties, and many of them have exhibited negative real permittivities in different optical spectral regime. So, specific focus is actually given to materials like silicates, germanides and metal nitrides, because they have relevance also in silicon CMOS technology. So, let us look further into silicates and germanides. Silicates and germanides, these are compounds of metals with silicon and germanium. They can exhibit metallic properties across the mid infrared and near infrared ranges. So, that is pretty wide range. These materials possess high DC conductivities due to large free carrier densities, but their optical losses are significant due to the interband transitions and high carrier relaxation rates. Despite these losses, silicates and germanides that can offer advantages for technological applications, as they are commonly used in silicon CMOS integrated ICs, and they can grow epitaxially on silicon substrates. So, that way fabrication wise it is much easier. Various deposition techniques such as co-deposition, chemical vapor deposition, physical vapor deposition, we will be looking into these techniques in the next lectures. Okay. They can be applied for fabrication of silicates and germanides. Etching techniques, both wet and dry, can be used for patterning and lift off processes with hard masks like silicon oxide or nitride are common in their fabrication. So, do not worry, we will cover briefly all these different methods of nanofabrication in the next 2 lectures. While silicates exhibit metallic behavior in mid infrared and NIR range and also visible ranges, their high loss limit their applicability in shorter wavelength. Okay. However, for infrared plasmonics they have good potential. So, next will be the metal nitrides. So, you can think of different metal nitrides like titanium nitride, zirconium nitride, tantalum nitride, okay, hafnium nitride. They also exhibit metallic properties in the visible and longer wavelengths. You can see here, yeah, they are metallic in the visible and longer wavelengths. So, that is good, and this kind of nitrides are non-stoichiometric. They are interstitial compounds with large free carrier concentrations. Here you can see the different optical images of the thin films of metal nitrides which are deposited on glass substrate, and these films are basically deposited by DC reactive sputtering. The thickness of the films is in the range of 100 to 120 nanometer, and you can see metallic luster, okay, from the films, and that is showing the possibility of the plasmonic behavior from these films in the visible spectrum. The color of the films correlate with the plasma frequency or the carrier concentration in these films. Now, with that we understood the different methods of creating alternative materials that can be beneficial for plasmonic applications in different frequency range. We can also look for different 2D plasmonic materials, okay, plasmonics with 2D materials, which is also referred to as flatland plasmonics, and it has gained a substantial attention after demonstration of plasmons in graphene. Two-dimensional materials like graphene they offer advantages over the bulk 3D materials, and that is why a lot of scientific research and applications have been demonstrated using graphenes. And the 2D material properties, the optical properties, they significantly differ from the 3D materials, and that leads to distinct plasmon dispersion relations. Now, these 2D materials are valuable in different applications including electronics, and they offer advantage of dynamic tuning of their properties through methods like electrical, chemical or electrochemical means. So, that is something which is really groundbreaking. If you can dynamically tune the properties of a device after fabrication, that makes it a very cool thing. Else you have to make a new device for all different applications, but if you are able to tune say the voltage and change the spectral response of a particular device that has got a graphene, so that will be very useful one, right. So, however, all is not good here as well, because there are challenges in synthesizing large area single crystalline 2D materials, right. So, 2D electron gas system, these are 2D electron gas systems, and they are also observed in other materials, not only in graphene. So, you can think of semiconductor inversion layers, semiconductor heterostructures, polar interfaces of oxides, and other 2D sheet materials like graphene, chalcogenides, perovskites and oxide nanosheets. Now, plasmons have been experimentally observed in these 2D electron gas systems such as semiconductor inversion layer, semiconductor heterostructure and graphene. However, in most cases these observations are limited to low temperature conditions due to high losses, and here the high loss is because of the low carrier mobility or high carrier scattering rate at room temperature. If you think of plasmons in 2D electron gas systems, they are primarily observed in mid infrared or longer wavelength range. So, plasmons in visible and NIR are not observed using these 2D plasmonic materials due to insufficient carrier densities. So, the behavior of plasmons in 2D electron gas can be understood through the dispersion relation, which are mentioned here. Okay. So, here you can see Ns is the surface charge density, epsilon s is the permittivity of the surrounding medium, m star is the carrier effective mass, gamma is the carrier relaxation rate that you see here, and Qp is the plasmon wave vector. So, in case of graphene, the carriers behave as if they are massless, and hence the dispersion relation is different. Okay. So, this is the plasmon dispersion relation in graphene at low temperature. So, here EF stands for the Fermi energy of single sheet graphene. So, if you take equation A that was shown here, A and B, this one, okay, this to allow us to quantitatively examine the characteristics of plasmon in 2D plasmonic materials. So, plasmon can theoretically exist in 2D electron gas at all wavelengths, but practical limitations may prevent their excitation and observation when the plasmonic wavelength becomes too short. So, let us do a comparative study. So, you can see that LSPR, localized surface plasmon resonance, was seen initially only for gold and silver in the visible spectral range, and by 2010 alkali metals also showed these properties in visible and UV, and now with ITO, SZO and GZO included in the list, they can also show localized surface plasmon resonance. This kind of nanostructures can show this in UV, visible and NIR. So, new materials are allowing people to explore the same plasmonic properties at different wavelength range, which was not explored before using conventional plasmonic materials. Similarly, if you think of tunable materials, silicon gave tunability in NIR and visible, germanium and 3,5 semiconductor also in the same range. With graphene you can explore infrared, okay, and with ITO, SZO and GZO also you can explore tunability in this range. Okay. For transformation optics, gold and silver if you use, you can only cater to the visible range, but with nitrides, ITO, SZO, GZO you can look after the NIR range, and with silicates and germanides you can also look for visible NIR and MIR, mid-IR range. For negative index metamaterials, you can see gold and silver again only in visible, with alkali you can get it in the UV, okay, and that is how different materials gave you options to explore the similar kind of feature or phenomena in different wavelength range. So, here is a summary of the things we have discussed today. So, noble metal you can use for LSPR, SPP and waveguides, negative index metamaterial, but they are not good for transformation optics and epsilon near zero effect, and they are not allowing you to have switchable metamaterials. Whereas metal nitrides, they can be good for SPP and waveguides and transformation optics. TCOs are good for LSPR and transformation optics, ENZ and switchable, but they are not good for negative index and SPP waveguiding, okay, and so on. So, you can actually go into this list and find out that which material is good for which particular application and then in what particular frequency range or wavelength range. So, let us conclude what we have discussed in this particular lecture. So, plasmonic materials play a crucial role in nanophotonics and metamaterials because they enable manipulation of light at nanoscale, and we have seen that noble metals like gold and silver are traditionally used in plasmonic applications due to their strong and tunable plasmonic resonance in the visible and near infrared range. However, these metals they suffer from high optical losses that limits their applicability in certain devices at shorter wavelengths. So, researchers have been looking for alternative plasmonic materials such as transition metal nitride, transparent conducting oxide, 2D materials like graphene. All these things are gaining more attention to overcome the limitation of the noble metals. Transition metal nitrides like titanium nitride, zirconium nitride, they also exhibit metallic property in visible and longer wavelength. TCOs like ITO, SZO, they provide low optical losses and they are good for transparent plasmonic applications. Okay. Graphene, a 2D material, also allows dynamic tunability of the plasmonic properties via electric field effect methods. So, you can bias the graphene sheet and change its chemical potential, and that can give you a different optical property, and that is very cool. Plasmons in alternative materials can be harnessed for different applications such as sensors, waveguides, super lenses and negative index materials. Resonant and non-resonant plasmonic applications will differ in their reliance on the localized surface plasmon resonance and the material properties, while noble metals excelling in resonant devices. So, while there is no single ideal material for all plasmonic and metamaterial application that you have seen, there is no one superhero kind of material, but you can keep looking for alternative plasmonic materials for a particular application and a wavelength range, and they can actually offer you promising alternative to the noble metals like gold and silver. So, with that we will conclude today, and in the next lecture we will look into the nanofabrication techniques. So, if you have got any query on this lecture, drop an email to me mentioning MOOC on the subject line. Thank you.